I'm glad to be the first to introduce you to the topic, and I see many faces here that people took my class, that I teach some of this, and collaborate with me, so good to see some familiar faces. Those who I don't know, I'm sure you're all at different levels, and many of you already have gone above and beyond what I'm going to talk today about, but it's good, I think, to be on the same page and be prepared for more advanced topics coming in the future. And I will simply cover the basic concepts of why do we need XAFS, why do we need X-ray absorption spectroscopy in general, for what applications, what are scientific drivers for that, and show some examples how to pose the problem, how to go about solving it, and what are the challenges. It will be impossible to use it as any kind of practical tool, but it will put you in the right frame of mind, I hope. And also, I teach a course once a year called Functional Nanomaterials, a graduate course here in Estonia. And those who are interested sign up. Next time I'll teach it before. And half of the course I talk about applications of XAFS to various nanomaterial topics. So today I will show some of them here too, just to be specific and not talk too general. I will focus on metal nanoparticles as just an illustration of some of the concepts here. So wanted to start with something I recently was asking myself. When Francis Crick coined his famous phrase, if you want to understand function study structure, what made it so difficult for me to do the same thing working with my nanomaterials? Why is it so difficult to study the structure of nanomaterials in order to understand their function? It seems to be kind of easy for Francis Crick. And I thought maybe I'll follow his footsteps and see how did he answer this question for DNA, because he was one who discovered the double helix structure of DNA, and what was the logic behind this statement. And the logic was, and I'm not a biophysicist, so I will be deliberately very vague and naive about that simply because it's not my field, but I did some reading to understand what was behind that, and I think that a few things we all understand, even if we are not in this field, is that the double helix structure helps explain why DNA has this functionality. So application, gene expression, mutation, and transcription, specifically due to the structure it's stable. Due to the base pairing of the nucleotide acids, it can be used for copying and transcribing information and read segments of genetic code. So this could be the very quick answer to the question why, in order to understand function, you need to study structure. That's why. So why is it difficult for nanomaterials? I'm bringing you to the case why do you need X-ray spectroscopy. It's not just general thoughts about something unrelated. So we're coming there. The question that we ask when we try to understand the mechanisms at the nanoscale is of the same nature. What are the structural units, descriptors, responsible for the material's functionality? And because of the lack of periodic structure, because of the lack of simple descriptors such as this 4 nucleotide bases, I said acids and bases, we have some unknown field to deal with. And if you read literature showing how people propose to deal with this, you will see various types of triangles, pyramids, and other structures connecting structure, processing, characterization, properties, or processing, properties, structure, function, and whatnot. And it's all published in papers, proposals, but it's not something I really understand how to follow. And this is why this field is up for grabs. Like, we don't really know how to understand nanostructure. There are no recipes, no blueprints to follow. Some of them are better than others, but in general, it's a very open-ended activity. That's why I like it. So that's the kind of my research is revolving around these issues. It's how to understand mechanisms of applied nanomaterials where the nature of activity is in the hidden details of atomic scale information. So I'm trying to understand how to uncover that. So in my field, I work with many types of functional materials, from catalysts to optoelectronics, to electromechanical, to filtration. Some of them are shown here: single atom catalysts, nanoparticles for catalysis, bimetallics, quantum dots for nanowires, hybrid with quantum dots, or some metal organic frameworks used for capture and decomposition of toxic agents, or novel actuators. In all of them, there is this mystery. Somewhere, there is a knob that if you turn it, it will work. But we don't know what that knob is, where it is, and how many knobs are. So in the case of single atoms, one would think, well, how many knobs can there be if there's just one atom? And if it does catalysis, this is it. But that was the naive thought, because it was soon understood that it's not that simple, because the catalyst may be coexisting with others located in different sites, some of them more active than others, and the descriptors could range from some strain in the local environment, bonding distances, and so on. So what it teaches us, these examples, is that in order to understand the functionality, you need to really go down with your tools to the nanoscale dimension. And XAFS is one of those tools. I wanted to start by showing a simple example of a stone thrown in the water surface, a pebble. And you will see, once you throw the stone in the water, the ripples will start spreading. And this is a simple example of a photoelectron that is excited. If you think of this as an inspiration to better understand X-ray absorption spectroscopy, it's only one part of it. The second part comes from the presence of neighbors around the X-ray absorbing atom. So there are two people kind of like exciting the wave interference by doing this, right? And you can see that if you want to use it as a structural tool, and you will change the frequency of this periodic motion, then the interference pattern will change, right? It will be different wavelength, different distances to the maxima and minima. And in principle, if you use it as a tool, like any tool involved in wave interference, it's used based on the same principle, you can then measure interatomic distance in the material if you have a probe that does this waving type of motion, right? Because by applying this to different geometries in which the distance between the atoms is different, the interference pattern will change. So if you want to measure this distance, you just look at this interference pattern and connect it to this distance. And if the distance is longer or shorter, the pattern will change. So there is a connection between how the waves interfere and what is the distance. So that's why it's a good structural tool, conceptually. Now let's see if it can be implemented in reality. So this is simply an example of single atom excitation, where the photoelectron wave is traveling away from the atom when it absorbs X-rays. When the core electron is excited, it travels as a wave in a quantum mechanical case, not classical case. And this is the wave that we are going to explore here. What will happen if the atom from which this photoelectron wave is excited, this atom, or one of them, I think this atom, what if this atom is surrounded by neighbors? What will happen to the wave? Same thing as what happens to the wave if it comes out of this person moving something up and down and hits the obstacle like a stone or obstacle in the water. That obstacle will become a source of secondary wave. That's what we know from classical wave optics. And this will become secondary process. Let's see how it works with photoelectrons. So if the X-ray photon hits the absorber, and the electron comes out, and then hits the electrons from the nearby atoms, they start oscillating. They start oscillating, sending the photoelectron wave back. That's how the scattering works. And this is shown by these arrows going back to the absorbing atom. And these two waves interfere in a very similar way how these two waves interfere. And so in principle, just like using this classical wave interference, you can learn about the geometry of the material. So you can do that in the nanoscale limit, where your waves come from the electrons, not from classical stones. So that's the gist of it. And in a more scientific language, The electrons may come from different shells. 4 electrons may come from K or L shells, 1s or 2s or 2p, and that really is defined by the source, the X-ray beamline that can reach, based on the energy available to the monochromator, it can reach a certain energy or not. And so by that we are tuning the energy to specific absorber electron level, and then by crossing the ionization energy and continuing above, we're going to excite the electron into the delocalized state where it can travel between the atoms, and the interference will affect how absorption coefficient behaves. Okay? Now, what is absorption coefficient? Absorption coefficient tells us how many photons pass the sample, or how many photons fluoresce as a secondary effect from the sample, from the sample. And the primary effect, the absorption, is proportional. The probability of absorption is proportional to the transition rate of the electron going from the lowest occupied state, the core state, to the highest, to the unoccupied state as a result of absorption. So the absorption coefficient, which tells us how many photons will be absorbed or not, is directly proportional to the probability of exciting photoelectron. However, this probability is not as simple as it looks here. So this is the absorption coefficient of different elements, chromium, copper, platinum, and they all have this absorption edge, which is the energy at which the photoelectron is excited. So the absorption goes up by a jump because it's a specific energy. And what is not shown here is that there is a fine structure past the absorption edge, and also in the vicinity of the absorption. And you will not immediately understand where would this fine structure come from, because the primary effect is like binary. Either electron is absorbed or not. So either the absorption coefficient is low or high. Below the ionization energy it will be low, above it will be high. But if you look more carefully, and this was done in 1930s, and I'll show the timeline when it was done, you will see that actually this region has some wiggles, some non-monotonic oscillations. In the edge regions, there's some shoulder here, there may be some features here, and also past the edge. So this is what we call X-ray absorption fine structure. That's why the technique is called XAFS, because of this fine structure. And there are 2 reasons for that. Maybe more than 2, but 2 main reasons how people are dividing this absorption coefficient in 2 regions in energy. One is called X-ray absorption near edge structure, or XANES, which is near the edge. That's why it's called near edge. And the second one is extended X-ray absorption fine structure, XAFS, which goes up to 1,000 to 1,500 electron volts above the absorption edge. And the nature of oscillations in the XANES region and the XAFS region is completely different. There's nothing to each other. So they are independently can be used for structural analysis. If anyone has a question, because I'm going to speak for almost the end of the hour, it would be nice to hear your questions at any time. So we don't need to wait for any kind of break. Just raise your hand. Let's make it informed. Yes, please.
I have a naive question. When you talk about electron wave, what's the particle of the electron wave?
It's what electron wave?
Electron wave,
It's a photoelectron wave, yes. So what is the question?
the question is, what's the constituent of that wave? It's like turbulence created by that electron, excited electron to the environment. Or
So this is okay. So this is not the wave as of matter wave like we used to see it in a classical case where we can see waves on the water surface. This is the effect that is introduced mathematically in quantum mechanics to describe the observations. For example, the interference of single electron from the slit or from 2 slits turns out to be similar how light interferes forming maximum and minimum on the screen. So that's why in order to describe it, we introduce the concept of a wave function. Wave function is a mathematical concept that allows to explain this by showing how the functions interfere. So the wave that I'm talking about is this type of quantum mechanical wave that was proposed by de Broglie to explain that at small mass and small momentum, all materials have this wave properties, and they don't behave just classical particles.
Oh,
So this is not the wave that we can actually catch in action.
yeah.
This is the mechanism that helps us understand this phenomenon, but it's very difficult to visualize it, to feel it, you know, in our fingertips, because it's not how it works. Quantum mechanics is where our intuition ends. We have to start using it as a mathematical tool. That's my feel about it. So when we see these waves, it's not that they're actually something waving, although it's a philosophical question, because nobody can detect them. Once you start detecting things, there's some other weird things will happen. But the overall observation of the phenomenon, including this fine structure, including other wave properties of particles, those observations support this model. So it's sort of indirect proof that the waves exist, but to catch them in action is not easy. Maybe not even possible. So, yeah, so this is theoretically, I already said that the absorption coefficient is proportional to the transition rate between two states of the electron, the core level and unoccupied state. And in the XAFS region, it's dominated by the density of states, which in the atom, of course, they are discrete states, right? Because electron can be either on one state or the other. There are molecular orbitals. So if you like it, you have good energy resolution, you can probe some maxima and minima and other features in the absorption rise of the absorption edge. And you can learn about materials density of state. It's not that simple, but it qualitatively can be done. And you can learn about difference between oxides, metals, and understand the coexistence of different structures. I'll talk a little bit more about it. In XAFS, in this range, people use it for completely different purposes. They want to understand the same way how we understand in optics from wave interference. They want to understand where the atoms are, what distance from each other. Based on the constructive or destructive interference, they interpret this spectrum just like we do it using X-ray diffraction or when we calculate film thickness by using interferometer. Same idea. You take the interference and learn about it from the distance. How to do it, I'll show very soon. The mathematical part here is the main foundation for this capability. Very briefly, because you asked this question about the foundational part, think about the electron excited from the core level. Even before you start thinking about it as a wave, think for a moment about it as a particle. What can you tell about its energy? Kinetic energy is related to the photon energy by conservation of energy. The photon loses part of its energy to excite the electron. What is left out is kinetic energy. So that's irrespective of whether it's particle or wave. This is conservation of energy. Then you turn in quantum mechanics and you think about the momentum as the quantity that is related to the wave property, the wavelength and the wave number of that wave. So this is de Broglie's equation. In fact, using XAFS as a playground, you can learn pretty much all fields of physics. Maybe not all, but a lot of basic fields. It's really great for demonstrating all concepts of physics. And then this wave has two parts in it, outgoing and scattered. And just like any interference, they combine. And because of that, they show the sinusoidal or periodic behavior as a function of wave number, just like any wave would when it's interfering with another. And so this sinusoidal behavior is the basis of determination of the distance between the atoms, because the maxima and minima will tell us what's the phase of the resultant combined wave, and from the phase we can get from the phase you can get R, and R is our distance. Nobody really does it like that because it's a much better way to understand the distance, to learn the distance, rather than looking at the maximum and minimum in the periodic function. And what would be the better way to do it? Who would suggest how else we can learn about the interatomic distance other than looking at the maximum and minimum of a sinusoidal function. In signal processing, we often use that. Fourier transform. If you take Fourier transform of a sine wave, you will get a single peak. If it's infinite sine wave, right? And that peak will be the frequency. And we are looking for frequency. For us, frequency is the interatomic distance here. So Fourier transform is the workhorse method of XAFS analysis. You take the data, you Fourier transform it, you already can run along. You can see if the peaks shift to the right, they shift to the left. That's like measuring the interatomic distance. You can use a ruler to measure how much the peaks shift, and that can give you a relative change pretty accurately. Nobody does it with a ruler, just say it. It's not that far removed from just looking at the data and telling what's happening. Although advanced analysis is very important for better understanding. So this is exactly what I found that as you change the photon energy, you change the wavelength of the photoelectron. And the condition of interference becomes periodic. If the two waves interfere constructively for certain energy or certain wavelengths, for example, giving rise to this peak, they will again interfere constructively when you continue changing the energy because the wavelengths will increase and it will be not 6 wavelengths on the distance between the atoms, but 7 or 8, another integer number. And that integer number gives constructive interference again and again. That's why you have alternating peaks, that's why it's periodic. So this is another way to think about it. And so to summarize this part, and again, anytime you have a question, please. So the information that is in XAFS, from what I think from what I already told you, we can already believe that this is true, that we can understand local atomic geometry. How can we do that using the concepts of XAFS? What is local atomic geometry? For example, the number of neighbors and the distance to the neighbors. It can be symmetric, it can be not symmetric. In principle, this information is there. The question is how to get it out, but we first want to know why to use this technique, because we want to know what information it can give us, and then how to get it. So the geometry includes number of neighbors. Why XAFS knows how many neighbors are around my absorbing number. It's not written here on the slide, but probably some of you can guess from what I already explained. So again, the question is, if my absorbing atom has 2 metal atoms, or it doesn't matter, metal or not, or 3 or 4 atoms of the same type, 3 different models are considered. Why would I get the answer from this experiment? How would I know based on the experiment that it's 2, 3, or 4? And why? What do you think? We already discussed why do I know about the distance? Because of the interference. Interference is connected to the distance. What is connected to the coordination? What property of the signal is connected to the coordination? Yes.
Probably the amplitude.
The amplitude. Why?
Because each one gives you the peaks that they're
Because they interfere,
right.
right. Because if the electron interferes as a wave, if it sends a wave to one direction and has a neighbor there, and the neighbor scatters this electron back, that gives sort of one act of oscillation, or in one contribution to the intensity of the oscillation. But if you have another neighbor, the same electron will be doubled how much it scatters back, or tripled. So there is a direct connection to the number of neighbors in the technique. And there are other things that we can learn about the geometry from in terms of this basic mechanism. Now, another question, maybe more difficult to answer, is why do we know from XAFS whether our neighbor is, let's say, the same element or another? Like, can we use it for understanding the composition of alloys, which contain different elements? Or all alloy components will look identical to XAFS. So it will not be possible to say whether it's just palladium all around, or palladium gold alloy. If you do palladium XAFS, yeah. Who can suggest an explanation? Well, I mean, the answer is yes, we can, but why? Yes.
Whether the energy, the X-ray, the electron you pick out with the X-rays, the energy it has is depending on the element, no? So you're only excited.
If you're doing it from palladium atom perspective, you always do it from palladium atom perspective. But the difference is that in one case it's just pure palladium nanoparticle, for example, in the other case it's palladium gold alloy. But in both cases you're exciting palladium core electron, so it's not that does not change. In both cases it will palladium core electron. But why will XAFS change when you measure it for palladium edge, whether it's monometallic or bimetallic palladium? So you're suggesting that, of course, if we measure it from a different element, the absorption edge energy will be different, but we're measuring from the same element.
You're not going to see the gold, right?
Well, if the neighbor is gold, in order to see it, something in the signal should change. Otherwise, we will not tell the difference. So what in the signal will change? We already discussed two things about the signal. The distance contributes to the phase. The number of neighbors contributes to the intensity. What information about the type of neighbor is encoded in this technique? You have
The
another
radii,
sorry?
so it's a different atom of different radius, which will change the distance to the neighbor.
Ah, but that still converts into the distance. So if the distance itself is the parameter, then we already know how to get distance from the neighbor. The question is the type. Basically, if in a hypothetical case, if you have a periodic lattice and you have either only palladium in the lattice or random substitution of palladium and gold, the distance will be the same. It's not direct case in real material. I'm just making it up, but you still can tell whether it's. So to make a story short, the scattering is not a simple process that you bounce the electron from the neighbor as if it's like hard walled. Even in the classical physics, the wave can interfere with a different phase delay. Not interfere, scatter back, because your boundary can be fixed or free. You know that from classical mechanics, right? So if you take the wave on a string and send it to the wall, and if it's a fixed boundary, it will come back with inverted phase, right? Because it has to make mid-boundary condition, but at the wall it should have zero intensity, right? So it comes inverted. If it's a free boundary, it actually will come in phase. So the phase depends on what the scatterer is. In the quantum mechanics, it's nothing like what I just said about the fixed wall, but the type of elements that we're scattering from affects the phase of the scatterer. And that can be used as a marker. Phase of scattering, which goes into the equation, is a marker of the, it's right here, delta. Is a marker of the neighboring element, and also what is called scattering amplitude, which is like a cross-section of scattering. For different wave numbers, different elements have different cross-section of scattering. That's another marker. So that's why XAFS has all these wonderful capabilities, such as local geometry, densities of neighbors, coordination numbers, atomic distances, one-length disorder. That's a very interesting concept, and you can, of course, learn how to analyze XAFS pretty quickly because it's really like software is so good and experiments can be done in a very reproducible manner. And if your material is pretty simple, you will get some answers. You will not know what they are, but you will probably get correct answers. So it's very important to understand what are the limitations in the theory that allows you to obtain these answers, because they are not hardwired into the material. They are depending on the approximations. For example, the disorder may come from two sources. If you have like a lattice, periodic lattice, there is no interatomic disorder because all atoms have the same exact distance to the neighbors, right? And that's what we will see by techniques which are not very sensitive to the local deviations from that lattice. But even in X-ray diffraction, we can see this result, because it will affect the intensity of the Bragg due to the Debye-Wall effect. This is because of the thermal ellipsoid that affects the displacement that causes displacement of individual atoms from the lattice position, even in the perfect lattice. And XAFS also has sensitivity to the disorder, say at the same time, because if the and here is something that probably I don't have time to discuss at length, but it also comes to question of like what a given characterization technique can do in terms of its intrinsic characteristic length and time. Of course, you cannot go and measure something with a short scale if you have a wavelength which is 2 orders of magnitude longer, right? Or you cannot measure something which can have period of atomic vibrations of the order of a few picoseconds if your characteristic time is nanosecond. But XAFS has exceptionally short characteristic time of the order of femtosecond. What does it mean, short characteristic time? The photoelectron, when it comes out of the atom, it does not continue this excited state for a long enough time, so that atoms that are probed by this electron will have enough time to vibrate, to move around, so that all their distances will be averaged out. It's not going to happen for the simple reason. These photoelectrons very easily recombine. Not photoelectrons, sorry. The excited, the core hole that is left in the core state when the electron is excited will easily be filled by high electrons performing reverse transition. As soon as this happens, the outgoing wave stops emanating, and the interference will be gone. You need two waves for it, outgoing and scalar. The reason I say that is because it's very short time, 1 femtosecond, which means that whatever you do with XAFS, you are making a snapshot. It literally is very fast snapshot of the local structural distortions captured at that moment. And when you do it for one absorbing atom or another absorbing atom, you have many, many snapshots. And they are uncorrelated with each other. That's why you have damping in your signal because of the dephasing of XAFS waves coming with different delays from each other. And the interference is not as perfect as would be. And this converts into the bond length disorder that can be extracted in principle from the data. And the charge state of absorbent elements affects the energy, affecting ionization energy of the core electron. And that can be used to sort of learn from this experiment what are the charge states of our atoms or ions of the experiment. So I wanted to show to you like a 30,000 feet view at research using XAFS, because you'll have more opportunities for more detailed training how to do it with different materials, using different methods. I think we should all be respectful to not using the same technique for anything any system we want, because we need to understand the applicability. As many techniques involved in X-rays or optical spectroscopies in general, XAFS is ensemble average. What does it mean? It has element specificity, right? Because if you tune your energy to a given element, you excite not one element, not one atom, but all atoms of the same element. Because all of them will simultaneously meet this resonance condition. The electron energy to excited will match the incident photon energy, and all of the electrons, not all, statistical process, but some fraction of them will be excited from all atoms in your system that are feeling the X-rays. And if some of them are in one environment, some of them are in another environment, and another one in a third environment, a mixture, right? You will have some reduced, oxidized, neutral atoms of the same element. The signal will have intrinsically weighted average of all of these environments. And if you think about it as some kind of representative structure, and you don't know about this heterogeneity, you can get very different results than the should be. Because it's like, averaging the temperature of the patients in the hospital. Some of them are fever, some of them are cold. The average temperature will not tell you anything, because there may be no patient like that with that temperature, and you don't know. So you need to really clearly understand whether your system is homogeneous or heterogeneous. And for two different types, there are two different methods of using XAFS for. How to understand that? You cannot just have a wild guess. There are other techniques. Either you know from the nature of the synthesis, and you can do some diffraction and study, obtain the presence of several phases, or you can do electron microscopy or other methods showing to you that you have coexistence of different states, then you need to use appropriate methods of XAFS analysis for this purpose, and you have to formulate your research questions appropriately, because you cannot use the same question for both types. So this is a case where you may have a good reproducibility between one atom environment and the other. Like if you think of each atom having various details of the local geometry, but all atoms are equivalent in that sense. You can still use average technique to understand all those details, right? Because you probe all of them and they give identical signal. You can average it out and you will get a representative species that you can understand. Like this is an example of blind man touching an elephant, but in our case, we are not that blind. For us, the most important thing is that these all are identical species. And we can understand them using this advanced analysis that you will learn in this series of workshops. And they range now how to use analysis. That's another branch. You can branch into different directions. And this is true about any technique, not just that. I divide them into forward modeling and inverse modeling. What is forward modeling? The research objective is you want to find the structure, right, of the material. And you have a spectrum. There are two things, spectrum and structure. You can go either in one direction or the other. That's why I call one of them forward, one inverse. In both cases, you can answer a research question. Suppose you start from the model of the structure. You don't have that model. I mean, you don't know what your structure is, but you may have some model. Then you calculate the spectrum theoretically and compare with experiment. If the theory and experiment agree, you may say that this model has credence, maybe the right one. Of course, it's better to compare with other models for which the spectrum may not agree. It will be even more reliable, but that's briefly what we all do when we do this forward type of model. It's always intrinsically subjective. It has strong model dependence. A better way to do it is inverse model. What's inverse model? You start from the spectrum. You start from the spectrum, you go to the structure, it gives you presumably a unique objective answer, if you like it. There are, of course, subtleties. You can go in the false minimum direction, but it's all nuances. But that's the conceptual difference between forward modeling and inverse modeling. And for them, we have many tools in XAFS how to do each. For forward modeling, primarily people use it for XANES. XANES is a black box. XANES has this edge features that come, as I said, from density of state effect, from some geometric effect, from many body effect, because it's not just a core electron that you're focusing on. It may interact with the hole and form an exciton. And this excitonic effect can contribute to the XANES and other things which are even more complex. So you cannot easily invert it using any kind of fitting. So people go in the forward direction. They start with some first principle programs, software, model this, and see if they reproduce it reliably. And if they do, that means their structural model is, that's how they say that this is correct, using this ISO. Inverse modeling usually involves fitting of some kind, right? Because how can you not use fitting if your objective is to find unknown parameters? You have to use fitting. So what I just said is very simple to me, but maybe you're confused about something. So again, let's hear you maybe objecting to this simple view that I presented, or maybe you have some other ideas. Maybe it's not that simple as I said. Anybody wants to say anything? It's not really so much about XAFS. It's generally how you understand nanostructures using some spectrum or signals. Then we go with heterogeneous systems. You get a sample that contains, for example, several catalytic species. Some of them may be not even active, but spectators. They may consist of single atoms, so nanoparticles, or larger clusters, or some agglomerates. And you don't know that they coexist. But that's one of the research questions, how to understand their speciation. And again, I said that if you treat it as a homogeneous system and try to apply this inverse or forward model, you will get absolutely different results than they should be. I'll give you an example. We all understand what coordination numbers are, right? Most of you, probably you should, right? Like, if I have two neighbors around me at the same distance, my coordination number will be 2. I don't know what theirs will be, but I'm caring for now, like with mine, right? Suppose that I have bimodal distribution of species in my sample. One species is a nanoparticle in which each atom on average has 4 neighbors. 4 neighbors. Okay? That can happen, right? Because some atoms on the surface have fewer neighbors, some atoms inside have more neighbors. On average, it will be 4. I'm just making it up. And suppose I have exactly 50% of my atoms in this nanoparticle structure. And the other 50% are all in the equilateral triangles, so that each atom has exactly 2 neighbors. Can you imagine that? Totally made up. But if you cut the system and you measure XAFS, what will be the average coordination number that you get? 4 and 2, 50% each. So what do you think will be the answer? What will be the answer from the experiment if you don't know that this is heterogeneous, but you think it's homogeneous, and you will apply these methods of analysis as if it's homogeneous? You will get coordination number average between 2 and 4, which will be 3, right? And then you will think, okay, I have a species in my sample that each atom has 3 neighbors. What kind of structure can it have? And I can come up with something in my mind that may explain that, and I will report it in a paper and it will be completely wrong because such species don't exist in my example, right? So what to do? You need to use completely different techniques and for different research questions. It's called speciation. You want to know how many different species are mixed together and what are the identities of each species. And whether or not you will be able to refine them precisely, it's not guaranteed because it's too much loss. So there are a lot of questions of this type. For example, in geochemistry, in catalysis, in environmental science, in many applications, you have coexistence of different species that change in time or in terms of response to pH, electrostatic potential, whatnot. That you want to understand the kinetics of these transformations or understand the speciation at different conditions. And you need to use methods that are ideal for that, which I will mention for later. And so now I want to switch toward more traditional topics, which many of you probably know. Can you raise your hands, please, who have already been at the synchrotron, at least once? Who has ever taken any course where you heard an explanation about synchrotron methods? Can you raise those who didn't raise their hand? So, or maybe I'll ask another question. Is there anyone who never heard about X-ray methods, synchrotron methods? Because I will then make a very quick introduction. So again, raise your hand if you've never heard about X-ray methods and don't know how synchrotrons work. Don't be shy. Don't say that. Because it's easy to explain, but since nobody really said that, I will go through this very quickly. So this is the idea how you can understand why X-rays are generated in the broadband spectrum, and this is due to the relativistic effect on the time dependence of electromagnetic field from the particle when it oscillates. And in the classical limit, you have just one frequency, and one frequency will affect the power distribution in this electromagnetic radiation. It would be simply harmonic. But in the case of relativistic particles, which is what happens when electrons are accelerated with an ultra relativistic speed, the spectrum is not sinusoidal, but it has this shape that causes Fourier transform to have many frequencies that look like this broadband spectrum, and this is what synchrotron radiation is. Then it sends we send it down the beamline pipe to the sample, but first we need to tune it to a certain energy because we need to use energy scanning. So this is all the mechanics of the X-ray absorption experiment. But there are other techniques such as spectroscopy and imaging, scattering and imaging that I'm not covering. And this is a typical slide where people show which techniques at the synchrotron are used for which purpose. And the typical beamline has the way to tune the energy, monochromator, and optical components such as mirrors, slits. And then for detecting, it's really the way to understand what absorption coefficient is. You need to measure the flux or intensity of photons hitting, coming at the sample and transmitted through the sample or fluorescent. So the geometry of the technique is not that difficult. It's what you do with this. And I will probably wrap up soon, simply going through the rest of the slides. This is some history here. The absorption edges were observed by Maurice de Broglie, Louis de Broglie's brother, in 1913. The fine structure in the absorption edge was observed by Frisch and Hertz in 1920. And chronic transformer from other chronic things. He proposed in 1931 that this fine structure is due to long range order, just like the attribute as a structure in the material that gives rise to interference like X-ray diffraction. But he turned out to be wrong because in the materials without long range order, this fine structure was observed. And it was first explained in 1971 by my postdoctoral advisor, Edward Stern, and others, his collaborators and students. And then this gave rise to a technique which recently celebrated its 50th anniversary. And it's a big deal. This technique turned out to be very useful for materials research. Here it just shows some kind of steps toward application to nanomaterials, which I'm going to skip, when it was used for the first time to understand nanoparticle structure, pretty much soon after it was discovered. In the mid-70s, few years from its discovery, the group from ExxonMobil already understood its potential for using XAFS for studying catalysts, because the catalysts are very good case for it. Because in catalysts, atomic coordination is limited to, it's not bulk. So you can use XAFS to tell what it is. So there are lots of know-how developed in 50 years in applying it in a clever way using some operando capabilities where not only you measure the data, but you also watch the functionality, the activity of the material to correlate structure and function. And many methods are developed for modeling data analysis that you will learn in this series. And this I already explained. And I wanted to show to you just, this I already explained. I wanted to show to you just, by the way, this concepts that I explained are all easy to find. Every single word I said, you can find tons of reviews on explaining this subject of XAFS. It's such an interesting topic. This technique is still, I will not say in infancy because it's 50 years old. There's so many things that are still improving. It's a lot of interesting opportunities for all of you to contribute using your research. And you have Nick here, who is expert in XAFS, and you can always go to him and Karina and others all here. And so there's so many good things that you can learn about it and even contribute. In fact, we're learning ourselves in our group how to understand different complicated things, and we develop new methods such as machine learning for answering this. This is the article that Nick co-led, where he summarized the methods. It's a review, a perspective on how to speciate those heterogeneous nanomaterials using XAFS, including machine learning methods. So that's something, just one example. Many applications of this technique simply because of its fundamental sensitivity to very general descriptors, coordination number, distances, disorder. You can imagine where they're useful for materials that may be changing their properties in a nanoscale that it's very hard to understand, like phase change material. They may restructure within just very few atoms, and you will change reflectivity so much that they can be used in optical memory recording. Or structural biology can explain how enzymes work. Or environmental science can understand how arsenic is migrating from water into iron oxide nanoparticles, and how does it happen and what's the mechanism. Or in catalysis, how catalytic sites work for converting reactants into products, phase transitions, some other topics, novel materials. Anything you want, you can probably understand from XAFS, but that's of course not true because some materials don't have that interesting question on the local scale, but you may not even be interested in trying. There are lots of resources. If Nick will share this slide, the links lead to videos that we teach during COVID. We have to put them all on the internet. And there are many resources where you can find a lot of links to videos, but better to ask the source, Nick, here, and others who can help you get started. And I want to finish with a question. There is a mistake in one of these figures. I'll tell you in which one of these videos, that does not as correctly describe XAFS as it may seem. Although the wave interference is right, everything seems to be fine, but something about it is off. What do you think is off? As far as does it correctly describe X-ray absorption spectroscopy? Who can answer? I mean, seems like the right one, right? Because the wave comes from the electron coming out, right? The two electrons, the electron wave interferes, form an interference pattern as if what you see on the wave surface, but still not the perfect analogy. What's not perfect about it?
Should there be some things in the water that the waves are bouncing off of?
Can you say it louder? Sorry.
Should there be like things in the water that the waves are bouncing off of that are interfering with?
Oh, but these are the, So there should be things on the water from which the wave should be bouncing off, right? So the fact that there are two people doing what they're doing does make an interference, but this is not what happens in XAFS experiment. In XAFS experiment, you have only one source of excitation, this guy. There is no second guy, the second curve. This is the obstacle. So the waves interfere exactly like in this movie, but the interference comes from the scattered wave, not from the second source. In real experiment, it's unlikely, it's impossible that X-rays will simultaneously excite two atoms next to each other. That's a subtlety. So it's about time. Maybe we can have a few more questions. Do you have any? Because it's almost time. Anybody? Any comments, questions? Yes.
Sometimes we can say the oxidation state by the XANES, but I don't know why.
So yes, absorption coefficient rising at a certain energy. And suppose that you want to compare two materials in which one element is the same element, but in one material it's more oxidized, and in the other it's less oxidized, or more reduced. The absorption coefficient in both of them will not be identical, but in one of them it will start at lower energy than in the other. So basically the onset of absorption will occur at different energy. And the more reduced the material, the more reduced the atom or ion that is the absorber, the more the absorption edge energy will shift to lower energy. And the reason is that the reduction means that it has on average more electron density. And that electron density is more efficiently screens the nucleus potential that attracts the electron to the atom, keeps the electron in the atom. The more screening, the less is the potential to overcome. It's like Mosley law. And so because it's less effective potential, the excitation occurs at lower energy. So that's why you can say roughly by looking at the edge position, what oxidation state is higher or lower, you can even calibrate it, not like a hard rule. Because for some materials, it's just not working as supposed. Any other question?
And so, some say that like in the middle, some say the top of the potential.
Yes, good point. There are three groups of people. All the researchers are divided in exactly three groups.
Yeah.
Group number one uses the position of the energy at exactly half of the edge length.
Yes.
Group number two uses the first derivative. And group number three uses the maximum of the peak. And they don't talk to each other. They're like, it's like religion, you know. So there's not much science in it. It's okay. It's no qualitative experience. Any other questions? Yes.
So you can use.
Can you speak all of that?
Oh, sorry. Because I just mentioned you can use like the XANES for catalyst mechanism elucidation, could you go into that a little further?
So I just explained that the principles that can be used to study oxidation state of materials for catalysts also. If it's some kind of oxide catalyst, it's more or less trivial. For metal catalyst, it becomes somewhat tricky because the electronic density may play tricks. Because on one hand, if you reduce your catalyst, it has more electrons, lowering the effective potential. But on the other hand, it rises the Fermi level. So it's kind of like increasing the level. Which one wins? I'm still not sure. So this is really a moot subject that is still overlooked by many opportunities for research. Thank you for your attention and interest.